When we think about this very large, range of edge AI applications and use cases, the way we think about it is that they all have the same architectural makeup. And so when we think about the building blocks of these applications, we can simplify this into three key components. The first is some sort of data connector, right? Whether it's a video stream that you need to pass through some edge AI model, or a collection of bespoke sensors, or machine data, audio data, text data. It's really important to understand not only how to digest and extract your data, but also format that and pass it through to the next critical component, which is the AI model or models itself. Really, this sits at the center of any AI edge application. And important to note that there may perhaps be multiple you have to manage. We'll talk about that later. And then finally, what I'll call a user interface. Now, this may be a physical user interface, perhaps a custom piece of software or application you build that will take some of the AI model insights and predictions, transform them into actionable, alerts and an impact. But it also may be something that you integrate into your existing IT enterprise software stack, whether that's some of the tools that we use on a daily basis, or sales CRM, enterprise communication software, or maybe it's something that happens under the hood that us humans don't actually even realize is happening. But the point is, there needs to be some way to, number one, feed your data in. Number two, run the model against that new data for inference. And number three, take the outputs and transform them into something meaningful, something impactful. So for the sake of the rest of this talk, let's start talking about examples and look at edge AI in practice. So taking those three components I just defined and described, let's build a simple AI edge application. So let's take this example. Something that we actually deal with on a day-to-day basis with a handful of our customers is automated defect detection in manufacturing, right? So if a manufacturer has one or a handful of human labor that's manually detecting defects in manufactured parts, small or large, that's highly manual, not very scalable, and ultimately not very reliable. So what if we decided to build an automated smart camera that can help make this process more efficient, more reliable, augment and enhance their existing process? Well, let's say that we have a camera in our manufacturing plant in the factory floor, and we have a little Nvidia Jetson device as well. And so that's going to be our device that we're going to essentially build a smart kind of edge AI, all-encompassing AI system. So the first is we'd want to connect to our video stream. That's something that the camera will take care of natively. We need to be able to pass that through to our custom defect detection model. So I'll walk through an actual example of this in a few slides. But let's take, for example, we've trained a YOLO defect detector. And then in this case, we're actually going to build a custom UI that will be useful for a site engineer or operator to be able to see the output feed with detections rendered on top of those initial frames, and then implement some sort of trigger, right? And whether that's a robotic process automation that will pull the parts off the assembly line, or human manually doing so. But that's really the impact of this system. And so, at the surface, this looks great. It's something that we can build. We can basically set it all up and configure it so that you can plug in the camera, and it essentially operates as a turnkey solution. And this may work great for us. However, when we start to look at this a bit more granularly and unpack what it takes, the building blocks to actually do something like this, yes, at a high level, those components are there and we can do that. But in practice and reality, there's a ton of complexity to set up a single smart camera. Take it from us, we've done this a lot with single board computers. I've got a few in my office. Seth has a fun little lab at home. Seth, I'd love to hear from you. I know you've got an anecdote about setting this up.
A few years ago, I had to get essentially a computer vision demo. It was a pre-built model, just up and running on one of Nvidia's kind of early Jetson dev boards, the TX2. It was, I don't know, probably about yay big. And so this dev board was built out to help provide computer vision research and development platform with the intention of builders taking that actual chip and then embedding it within their systems. Just trying to run a computer vision model on this system, it took probably 6 hours to just get the device configured so that we could run the model. And every step along the way was hit with hurdles, from installing the operating system itself, ensuring all the drivers were compatible with the hardware that was available, downloading all of the dependencies, making sure I had the right version of Python to run the model with the versions of the dependencies that were needed, connecting the video stream. And so, we did this for one demonstration just to prove out a concept. If you're building an edge AI strategy that requires, someone to do that by hand multiple times, it creates a real bottleneck, and it's a real pain in the neck to get those systems up and running the first time.
Yeah, no, absolutely. And like more specifically, as Seth was saying, that there's the device level. You have to install an operating system. What system level dependencies are needed? A really important consideration, and actually something that becomes very complex when you're thinking about an all-encompassing edge AI app, is resources and resource constraints. If you have a model and a video connector and an app and some sort of automated trigger running on the same device, how are you going to effectively allocate RAM, number of CPU cores? Is there GPU accessible? If so, do you have CUDA installed? Do you have the right drivers installed? So that can, there are a lot of factors that make that very complex and certainly not scalable. So if you wanted to build this solution, once, great, but dozens of times, hundreds of times, it becomes a bit more impractical. So, because of a lot of these layers of complexity, we, in our experiences, we came up with a different approach that will allow you to more easily scale your edge AI apps. As I go into this slide, what we've done is we've distilled our experience down into 8 principles that make up this framework that we believe applies to a wide range and spectrum of edge AI use cases. So I'll just note real quick that we're going to publish these principles. They're part of a broader white paper that we're working on that, as a thanks to joining this webinar, we'll make available to you. So stay tuned for that, after this webinar. Seth, I'd love to hear some of your thoughts, but 2 thoughts before I do on these principles. What we've done is we've created these technology agnostic principles that make your edge AI app design most efficient, most scalable. The 2 that stick out to me are the idea of separating your application code from your model code and separating that logic. And there's a series of downstream effects that has that we'll show a little bit later. The second, maybe more of a implementation theme than it is a principle per se, is the idea of containerization. And fundamentally, containerization of your apps, of your models, of the different components will kind of, by default, incorporate and apply a lot of these principles. Seth, what are your thoughts on some of the key takeaways in a nutshell of the principles that we've come up with?
Yeah, I think, Brett, one of the biggest things that we've seen working with our customers and working with members of the open source community that we're connected with through a couple of the projects that we sponsor, is just a recognition that doing things by hand becomes really laborious. And so these principles are really kind of a mindset shift that you can take to whatever edge AI problem that you're facing. And use them to maybe come up with a new pattern that's going to work and scale within your environment. And I think one of the big themes here is really being thoughtful about what IT and OT operators need to do their jobs efficiently and well. And so if you're able to create an architecture and build out a system that, 1, hits its latency requirements, but 2, is maintainable, that's going to create a lot of downstream efficiency gains. It means that you're going to be able to improve and update these edge systems over time. It means that through smart architecture, components can be individually addressed and touched up and improved upon without having to re-implement the entire system as a whole. The use of microservice type thinking as opposed to monolith type thinking is a real boon, especially for edge AI. And one of the main reasons is because edge computing hardware is often comes at a premium. And so you want to take advantage of the really high-end hardware for just the high-end computing you need to do. And then wherever possible, hand off sort of standard computer code to kind of lower-end hardware using connections to make all that work. So please feel free to use these principles and find interesting ways to apply them. And what's great about the rest of the time we'll be together today is we're going to be showing you some examples of how we implement these principles in different design patterns with a couple of use cases from our customer experience.
That's a great transition into revisiting this defect detection app that we just talked about a few slides ago, right? While I mentioned that that solution would certainly work, it may be cumbersome and complicated to build one time, but trying to scale that out becomes very impractical. So if we were to reimagine and redesign this solution, here's how we would do so. And I'm going to follow this with an actual demonstration. So let's say that instead of having every component, right, the data connection, the AI model running, and the web UI running on the same smart camera, instead we're going to separate things out of it. So on the left, we see that these models and the video connectors will be running on the device, or perhaps multiple devices on the factory floor. And then through containers, we can actually containerize the UI. We can, through protocols and networking, access that data through a different system, through a different environment in our enterprise software system, whether that's the cloud, prem, or elsewhere, and have our web UI access there that will showcase some of the defects and then ultimately lead down to some sort of impact, some sort of action, which would actually ultimately be triggering some robotic process automation to pull the defective part off the assembly line for further inspection. Now, a few of the principles at play here are the separation of model logic and application logic, number one. This means that the AI model is running and should limit the number of times you have to manually interact with that edge device. And instead, focus on your application. Any tweaks you need to make, you can do so without having to worry about kind of crashing your entire system. So I think I mentioned a few in there. Protocols is another big one, and networking stability and reliability are some of the principles that we've uncovered here. So without further ado, I'm going to share my screen now. Let's see here. And walk through an example of how this is actually implemented. So on my screen, you should see the Modsy interface. What we see here is actually a device group that we've created for a custom defect detection model. What we did was we printed some 3D gears, some spur gears, for the sake of a prototype that we helped build out for a customer to prove this concept. We then created a data set. We'd manually defected some of the parts, labeled it, trained a custom YOLO model, and through some of the mechanisms that Modsy makes available, deployed that model into our central library. So you can think of Modsy here as the place that we're storing and queuing these models before we send them out remotely, to different devices. So we've got our defect detection model here. I'll give you a sneak preview of what the spurs gears look like, where we're trying to detect defects or things that are wrong with these gears. Now, we also see some of the information available to us about this model. More to come on that later. And then what we've done is we deployed this out to an Nvidia Jetson Nano device running in SES Office, and we've containerized the application part. So I'm running that locally in my office here in Philadelphia, and we see that there is a healthy status. That's because there's actually a steady communication tunnel between Modsy Enterprise and that Jetson Nano. If I just pull up my terminal real quick, you should see a lot of logs running. That's because it's making predictions. This is the logs of the Nano itself, making predictions in just a couple milliseconds. And what we're doing is we're feeding those back through to the application that we're actually using to monitor this capability on my screen right here. So this is something that a site engineer and operations manager, as I mentioned, somebody who's actually in charge of manually doing this today, could use to greatly accelerate and enhance their existing processes, make their lives a lot easier. We see the overhead view of a plate spinning with these custom-made gears. This kind of resembles and simulates the assembly line for automated QA and QC. And then we've got some of the predictions being shown live. And just to show you guys what this looks like, from the front point of view, there's a Jetson Nano right here running. So, this is powerful because for several reasons. Number one, I've containerized this. I'm running this completely separately. So if I wanted to make any changes to the UI, I could do so no problem. Something else that I will go back to in a second, is this gives me the ability to stream results from multiple cameras across the factory into a single centralized, operations dashboard and management piece. Something that would not be available if this was all baked into a single smart camera.